Good day everyone, this is Renz Malabote, my video demonstration in the exercises in my workbook. Now let's proceed our objectives. At the end of the video, you are expected to define and explain the conditions required for a series to satisfy the alternating series test. Second is to apply the alternating series test to determine whether an alternating series test is converges or diverges. And lastly, you are expected to estimate the sum of a convergent alternating series by using the alternating series estimation theorem to find the error bound. Let's start with the alternating series test. An alternating series is a series where the signs of the terms alternate. That means they switch between positive and negative. It looks like b sub 1 minus b sub 2 plus b sub 3 minus b sub 4 plus b sub 5 minus b sub 6, and so on and so forth. Now, for this series to converge, it must satisfy two important conditions, which is the first conditions must be the terms must approaching to zero as n goes to infinity. That is, the limit of p sub n as n approaching to infinity must be equal to 0. And the second condition, the terms must be decreasing. That means each term is smaller or equal to the one before it. If both conditions or if both of these conditions are true, then the alternating series converges. So we have the problem, the summation of negative 1 raised to the power of n minus 1 all over 7 plus 2n from n to 1 to infinity. This is clearly an alternating series with our bn be equal to 1 over 7 plus 2n. It is obvious that the bn is positive, and so we know that we can use the alternating series test in this series. It is very important to always check the conditions for a particular series test prior to actually using the test. One of the biggest mistakes that many students make with a series test is using a test that did not meet the conditions for the test, and that is why they get the wrong answer. So let's take a look at this limit. So you have the limit of bn as n approaching to infinity. So we substitute our bn, since our bn is this, so we have the limit of 1 over 7 plus 2n from n to infinity. And so we apply directly the limit. So we have 1 over infinity, it must be infinity. So by the limit theorem, we know that whatever number numerator divided by the denominator, which is infinity, would be equal to 0. So the limit is 0, which first conditions met. Now let's take care of the decreasing check. In this case, it should be strictly or pretty clear that 1 over 7 plus 2n is greater than 1 over 7 plus 2n plus 1. Since like obviously when we substitute number, like for example 1 over, let's say n would be equal to 2, we have the original function is, the original series is the greater than the next sum. So we have 7 plus 2 times 2 is 4, 4 plus 7 is 11. It's always greater than 1 over, since we have 2 here, so 7 plus 2, 2 plus 1 is 3, 3 times 2 is 6, so we have 6 plus 7 is 13, which is the higher the denominator, the lower the value. So we can say that it is decreasing. Therefore, the Bn form, this Bn form is decreasing sequence. So with these conditions in the alternating series, both are met, and so the series is convergent. Let's move on to the alternating series estimation theorem. This theorem helps us to estimate how close a partial sum is to the actual value of the series. Let's say S is the sum of the entire alternating series, and the S sub n is the sum of the first n terms. Then, the remainder or error written as the absolute value of R sub n equal to S minus S sub n is less than or equal to the next term, B sub n plus 1. In simple terms, this means the error we make by stopping at the nth term is no bigger than the next term in the sequence. So we have this another problem, the summation of negative 1 raised to the power of n plus 1 over n cubed from 1n to infinity. So first, let us check the conditions. The condition should be the limit should be equal to 0 and the series should be decreasing. So we have the limit of an as n approaching to infinity must equal to 1 over n cubed. Now we have to rewrite the limit n approaching to. So we have limit of n approaching to infinity 1 over n cubed. So obviously it equals to 0. Now, to check if this series is decreasing, we will manually solve it. So we have, if our n is equal to 1, obviously we have 1 over 1, which is greater than 1 over 1 cube is 1, so they are equal. And if n is equal to 2, so we have 1 over, it must be 1/2 because 1 over n plus 1 cube. 2 times 2 is 2 times 1 plus 1 is 1. 1 plus 1 is 2. Raised to the power of 3 is 8. So obviously it is decreasing because the original series is pretty much higher or larger than the next series. Now we can proceed to estimate their sum. So you have the formula, the finite sum minus the partial sum is equal to the error, which is lesser than the a sub n plus 1. In our error, we will be assuming it would be 0.001, which is our an plus 1. A sub n plus 1 is n plus 1 cube. 1 over n plus 1 cube. So we will raise both sides into -1 to eliminate the numerator 1. So we have -1, -1. This 0.00 raised to -1 is 10,000. And this will become n plus 1 cube. To eliminate this, we will get the cube root of both sides. The cube root of 10,000 is 21.5, and this will become n plus 1. To eliminate 1, subtract both sides by -1. So we have 20.5, which is greater than n. So let's get the whole number. So we have 21 equal to our n. So we need the 21st term of this series to get our finite sum. So then we can have the a sub 21 should be equal to 1 over 1 cube. Negative, it should be negative, right? The positive. Negative 1 over 2 cube plus 1 over 3 cube, and so on and so forth. And so on and so forth, plus 1 over 21 cube. If we approximate this all sum, if we add that all, we can have 0.90159. Since we just need the 4 decimal terms, so we only have 1, 2, 3, 4 in that value. So we will round up this value. So we have 0.9016 is our the approximate sum of this series. So we have the problem. Let's find the approximate sum of the -1 raised to n plus 1 over n raised to 5 as n from 1 to infinity. So first is we need to satisfy the conditions first. If it is convergence, the conditions are the limit of an should be equal to 0 and it is decreasing, so that it is convergence and we can find the approximate sum of the series. Now let's proceed to the first condition. In first condition, we have the limit of an as n approaching to infinity. We can have the limit of 1 over n raised to 5 as n approaching to infinity. So we apply the limit 1 over infinity. So since we all know that based on the limit theorem, 1 over infinity is equal to 0, and that the first condition is satisfied. Now we take a look at the second condition. It must be decreasing. So here we manually solve it. So so that we can show that it is really decreasing. So we have a sub 1 be equal to 1 over 1 raised to the power of 5, approximately equals to 1. A sub 2 is equal to 1 over 2 raised to 5, approximately 0.031. And a sub 3, 1 over 3 raised to 5 is approximately 0.001. And from that, we can say that the a sub 1 is greater than the a sub 2, and a sub 2 is greater than a sub 3, which is pretty much decreasing. Therefore, we can say it is convergent, and we can find the approximate sum of this series. Now, we can have the formula. So we have the absolute value of the infinite sum minus the partial sum is equal to the error, which is lesser than or equal to a sub n plus 1. So since we all know that our an a sub n plus 1 is 1 over an plus 1 raised to the power of 5. So we have this. We will be using the error of 0.001, which is lesser than or equal to 1 over n plus 1 raised to the power of 5. Now, let us power the both equation into -1. So we have 0.001 raised to the power -1 and the other side is 1 over n plus 1 raised to the power of 5 raised to -1. So that this numerator 1 will be eliminated. If we calculate this, we can have a answer of 10,000, which is lesser than or equal to n plus 1 raised to the power of 5. Now we get the fifth root of this both equations so that this 5 exponent will be eliminated. So we have the fifth root of 10,000 and the fifth root of 9 plus 1 raised to the power of 5. If we simplify that, if we get the fifth root of 10,000 is equal to 6.31, which is lesser than or equal to n plus 1. To eliminate this 1 so that the remaining variable is n, we will using the addition property of equality. So let's subtract -1. So we have n 6.31 minus 1 and the other side is n plus 1 minus 1. We get a final answer of 5.31 lesser than n. Since we need a whole number to get the number of terms, so we need to get the whole value of whole number of this 5.31. The whole number of 5.31 is 5, and that is the value of our n. And we need the fifth term of n so that we get the approximate sum. By that, we can now have this s sub 5 equal to 1 over 1 raised to the power of 5 minus 1 over 2 raised to the power of 5 plus 1 over 3 raised to the power of 5 minus 1 over 4 raised to 5 and plus 1 over 5 raised to 5. And if we calculate this in the scientific calculator, we can have the approximate of 0.97208063. And since based on the direction, we only need the 4 decimal places, so we will round off that into 4 decimal places. So we have 0.9721. And that is the approximate sum of this series. Let's proceed to our another problem. We have the summation of -1 raised to n times n over 8 raised to the power of n from 1 to infinity. So let us check first the conditions if it is equal, if the limit is approaching to 0, and it must be decreasing so that it converges. Therefore, if converges, we can get the approximate sum. So in this, we have first find the limit of a sub n. So now we have the limit of n over n raised to n as n approaches to infinity. If we apply that, we can have this infinity over infinity, and this is in the indeterminate form. If it is indeterminate, we can apply the L'Hopital's rule. So we differentiate the numerator and the denominator. So we have this, the limit of 1 over 8 raised to n as n approaching to infinity. If we apply the limit, so it will become 1 over infinity, or 1 over infinity is equal to 0. And we need to test if this series is decreasing. So we again manually compute it. So we have this a sub 1 be equal to 1 over 8, which is approximately 0.125. A sub 2 is 2 over 8 raised to 2 with approximation of 0.016. And a sub 3, 3 over 8 raised to 3 with approximation of 0.0005. And we know that it is decreasing. And this, we can now get the sum. As we have observed, so from this series, as we have observed, we can rewrite that into 1 over a or 1 over 8 raised to n. And it is a geometric series with a common ratio of 1 over 8. In geometric series, we have the formula to get the sum, which is, the sum is r over 1 minus r raised to the power of 2. And that we can substitute r to 1/8, the common ratio. So we have 1/8 over 1 minus 1/8 raised to 2. And now we will simplify that. We now have 1 over 8 over 7 over 8 raised to 2. Squaring this, we have 1 over 8 over 49 over 64. And simplifying this, we can have getting the reciprocal of that, so that, and proceed to multiplication for us to easier to get the product. So you have 1 over 8 times 64 over 49. Then we can have 1 times 64 is 64. 8 times 49 is 392. If we calculate 64 divided by 392, we get the approximation of 1632,65306. Since based on the direction, we only have the 4 decimal places. So we can have the approximate sum of 0.1633. And this is the approximate summation or approximate sum of the series negative 1 raised to n times n over n 8 raised to n. So we have now this problem. We will get the approximate summation of this series. So we have the negative 1 raised to n times n raised to n over n factorial from n equals to 1 to infinity. So first thing to do is we need to check the conditions. So by direct computation, we have this negative 1 to negative 4.5, 10.66, and so on and so forth, negative 2604. So look at the term, the magnitude of this series, n raised to n over n factorial. Using this direct computation, we can say that it grows extremely fast. Like for example, these terms. Then the terms is pretty, it is not approaching to 0. Then in fact, it is approaching infinity as n getting larger and larger and larger. Hence, the series diverges. The terms do not go to 0, which is in fact the bn or the an is approaching infinity as n grows. The necessary conditions for convergence, which is the limit of an should be approaching to 0, fails. Therefore, we can say that this series diverges, and And if it is diverges, then we cannot approximate the sum, or it has no infinite sum.